All right, in this section, we are going to work on finding the areas of two-dimensional figures. We start with just sort of a list of these formulas. I'm going to spend just a few minutes talking about these formulas. They're not anything you need to memorize. You'll be able to have access to a sheet of formulas. I do always encourage people and say, you know, it's good to be able to recognize the formula that you need to use, right? So if you had a sheet of formulas that were not labeled, it's going to be able to recognize, you know, kind of pick out the formula that you would need to solve a problem. So we have some basic formulas. Some of them we've already know, like the triangle formulas we know, right? That the area is 1/2 base height, or that if I don't have the height, I can use Heron's formula, and here S is half the perimeter. We already know how to find the area of a circle, and, you know, bonus fact, we know the circumference as well. The area of a rectangle, you probably already know that the area of a rectangle is given by length times width. A square is just a rectangle, but all the sides are the same. With a parallelogram, we find that area by taking base times height. It looks similar to the formula for a rectangle, but just note that you're not multiplying the two side lengths. The height is always perpendicular to the base. All right, so you have to know that height to get the area of a parallelogram. A rhombus is just a parallelogram with 4 equal sides. And a trapezoid is basically a triangle, like with its head cut off. The top and the bottom, we call these both bases. So there's 2 bases, and they're parallel to each other. And then the other sides don't need to be parallel. So the area of a trapezoid is 1/2 the height times the sum of the bases. So we're going to do some examples. I usually like to approach these just by kind of picking apart the pieces that I need to put together. So here, if I want the area of this figure, it says it's a right triangle with a semicircle appended to one side. So the area, to find the area, I'm going to need to find the area of the triangle and an area of half that circle. So say 1/2 the area of a whole circle. We know the area of a triangle is 1/2 base height. And the area of a circle is pi r squared, so 1/2 pi r squared. And we know, if I look at this figure, right, they gave us the base of 9 centimeters, and then they gave us the hypotenuse, 15 centimeters. I need to get the height, right? I need to have something I can plug in for height in the area of the triangle. But we can find that. We know how to find that. We've been doing that since the first chapter. We can use Pythagoras. So we know that h squared plus 9 squared is equal to 15 squared, which means that, let's see, if we subtract, we get h squared is 15 squared minus 9 squared. And then we'll take the square root. So the square root of 15 squared minus 9 squared is 12. Note that it's not 6, right? We cannot split up a radical over addition or subtraction. So it was important for us to actually plug this in or figure out the value of 15 squared minus 9 squared. So we get 12 as a result. That's 12 centimeters. And then there's another value that we get now, a bonus value that we also need actually in this problem. The height is the diameter of that circle. So the height is actually twice the radius. So if I know that the height is 12 centimeters, that means I know the radius is 6 centimeters. Now we have everything we need to plug into these formulas. So we have 1/2 times 9 centimeters times 12 centimeters. Plus 1/2 pi times 6 centimeters squared. Notice that in both of these terms, my units are going to be square centimeters because I have centimeters times centimeters. Let's see, let's do some reducing. 1/2 times 12 is 6. 6 times 9 is 54 square centimeters plus 1/2 pi. 6 squared is 36 square centimeters. 1/2 times 36 is 18. So what we have is 54 plus 18 pi square centimeters. There it is as an exact value, and then we can approximate. (110.55). And there's the area of our figure. So we had to find this area by basically putting together the pieces. There were sort of two composite pieces that we added together to get what we were after. In this next example, we want to find the area of the shaded region. It looks like an arrowhead. Of course, we don't have an arrowhead problem, but you know, if we sort of examine this a bit, we can see that what we really have is a big triangle, right, whose bottom is the dotted line, and that we're cutting out this smaller kind of embedded triangle. So the area that we want is the area of the big triangle minus the area of the small triangle. Both of these are triangles, so I'm going to use 1/2 base height for both. But of course note that they have different heights. They in fact have the same base, right? They both have a base of 12 centimeters. But they do have different heights. So maybe I'll call that the height of the big one and the height of the small one. Just so that they don't look like terms and we don't call it 0. Alright, so for the big triangle, the height is going to be the sum of 9 centimeters and 4 centimeters. That's 13 centimeters. That's the height of the big triangle. And the height of the small triangle is 4 centimeters. Alright, let's simplify a bit. Half of 12 is 6. I can do that in both of these terms. So 6 times 13 is 78. So 78 square centimeters minus 6 times 4 is 24. And then subtracting gives us 54. 54 square centimeters. No need to approximate here. We have a nice exact value. Alright, one more example in this section. We want to find the area of this figure. They tell us that it's a trapezoid surmounted by a parallelogram. So the trapezoid's on the bottom. I know if I want the total area, I'm going to do this by finding the area of the trapezoid and adding it to the area of the parallelogram. The area of a parallelogram is given by base times height. The area of a trapezoid is 1/2 times the height times the sum of the bases. So for the parallelogram, the base is this 15 centimeters, and that's perpendicular to this height of 6 centimeters. So that's 15 centimeters times 6 centimeters. And then 1/2 times the height of the trapezoid is 7 centimeters. And then we need the sum of the two bases, so 20 centimeters plus 15 centimeters. Alright, so starting out, 15 times 6 is 90. So we have 90 square centimeters for the parallelogram. The trapezoid, 1/2 times 7 centimeters times 35 centimeters. And that is 122.5. And then all together, oops, 212.5 square centimeters.